Hello everyone, I'm Miles. In the age of AI, we need statistics to understand data, judge evidence, and better understand and use AI. Today, we'll learn as we go, using a real-world problem to connect the core concepts of statistics. Does more weekly study time lead to higher final grades? There are 800 students in the course. We randomly select 12 and record their study time, final grades, and previous GPAs. Study time is the independent variable because it might explain the change in grades. The final grade is the dependent variable because it's the outcome being studied. Previous GPA might be a confounding variable, and students with a better foundation may have different study habits and find it easier to get high scores. Therefore, even if study time correlates positively with grades, it doesn't prove study time is the sole cause. All 800 students are the population, the 12 selected are the sample. The average grade calculated from the sample is a statistic. If calculated for all 800, it's a parameter. Remember, samples correspond to statistics and populations correspond to parameters. Now for the grades, the total score for the 12 people is 955. So the sample mean is 955 divided by 12, which equals 79.58. The mean tells us the central location, but we also need to know the dispersion of the data. The sample variance is about 109.17. The sample standard deviation, the square root of 109.17, is 10.45. This means a typical grade differs from the mean of 79.58 by about 10.45 points. Looking at the 5-number summary, the minimum is 62, the first quartile Q1 is 72.5, the median is 79, the third quartile Q3 is 86.5, and the maximum is 99. The interquartile range, or IQR, is Q3 minus Q1, which equals 14, meaning the middle 50% of grades fall within a 14-point range. A box plot uses these values to show the center, dispersion, and skewness of the data. This data is roughly symmetrical, but slightly right-skewed because the mean of 79.58 is slightly higher than the median of 79, and the right side extends further. In a symmetrical distribution, the mean, median, and mode are usually close. When right-skewed, the right tail is longer, and the mean is usually higher than the median. Left-skewed is the opposite. Now assume that in a larger, similar group of students, grades approximately follow a normal distribution with a mean mu of 80 and a standard deviation sigma of 10. Applying the 68, 95, 99.7 rule, 70 to 90, which is mu plus or minus 1 times sigma, accounts for about 68%. 60 to 100, which is mu plus or minus 2 times sigma, accounts for about 95%. 50 to 110, which is mu plus or minus 3 times sigma, accounts for about 99.7%, so only 0.3% fall outside this range. Since the normal distribution is symmetrical, about 0.15% are above 110. Finally, a student scores 95 points. To calculate the z-score, z equals x minus mu divided by sigma, which is 95 minus 80 divided by 10, equaling 1.5. This means their score is 1.5 standard deviations above the mean. That's learning as we go, identifying variables, distinguishing population, sample, parameter, and statistic, calculating mean, variance, and standard deviation, using quartiles and box plots to summarize data and judge distribution shape, applying the normal distribution rule, and finally using z-scores to standardize specific grades. Statistics isn't just isolated formulas, but a complete thinking process from data to evidence.